Okay, so I'm going to talk a bit about some stuff I've done and then what are some things I'm interested in doing here. So this is kind of a very messy talk which involved drinking 5 cups of coffee, which is probably a bad idea. Of course, mathematicians will know that they're machines for turning coffee into theorems, and computer scientists know that we're machines for turning coffee into code. So really I should be coding, but unfortunately I'm having to talk, which means that you're going to get the wrong effect. Okay, so as was said in the introduction, I've been in Cambridge since 2001. We've done various things in the computer science department. We're the faculty of computer science. We're called a computer laboratory for weird historical reasons. We used to be part of the math department, and we built machines for doing mathematics out of coffee, and so we were the mathematical laboratory, and then when we split, we became the computer laboratory. We were a computer science department. Stuff we've done, I build stuff, as was said, and was one of the various people that built some of the stuff that is cloud computing. So we built a thing called Zen, which is the hypervisor, which virtualizes the hardware, so you can run multiple instances of Linux or Windows or whatever on the hardware, and that's what Amazon use for their cloud service. And more recently, we've spun out a thing which is a kind of rather nice thing called unikernels, which is an operating system that's written, it's a library operating system written in OCaml, which some of you may know, functional language which has some nice properties, and we built a bunch of useful things using it, which then became part of Docker. Docker is a company which builds containers, which are also a big part of the sort of cloud infrastructure out there that many people use, including Microsoft and Google and eBay and a few other small companies like that. And other stuff I've been involved in, I got peripherally involved in the Raspberry Pi. It's a tiny little computer, which we originally did because we got annoyed with MIT, who had this project called the One Laptop Per Child, which was a $200 laptop, which you could buy for $100. And we said we could do that for 10. And we didn't quite make it. It cost 15, but never mind. And now there are about 10 million of them out there, which is quite a success story. So Eben Upton, who was at Broadcom, ran with that. But I was in this little group that we came up with. The name, if you're interested, came from the idea of we were blowing a raspberry at MIT, if you know the English expression. I think, you know, if you count the numbers, we won. And another thing I peripherally got involved in was computing at schools, which is introduced a curriculum into schools in the UK so that we actually teach computing, not IT. And we think that's going reasonably well. The big task, of course, is getting enough teachers to be able to teach. So we actually have one teacher in East Anglia. She taught a huge class of 11 to 13-year-old girls how to teach. They'd learn how to program, and they now teach other kids, teachers, and parents, which is very subversive and cool, I think. Anyway, before I was in Cambridge, I was at UCL, and I was in Peter Kirstein's group in computer science there in the Pearson building. And back in 1980, that was actually the stats department. So again, I was in a department, came out of stats, very ATI, Turing Institute-ish. Named after the Pearson, and had all kinds of luminaries there, including some dodgy people who did eugenics, but let's ignore that. And one of the things we did there was we were involved in putting the first internet routers in Europe up and building stuff and connecting stuff together. And then before the 80s, I was in Cambridge doing physics. So occasionally, if somebody here shows me something mathematical, I don't run screaming from the room, but it may take me a while to remember how tensors work and stuff, but, you know, have done that. So I'm 50% here, which I think one of the highest percentages. This is mostly, as I was just explaining to somebody, to the next speaker, I actually live 7 minutes up the road by bike. So being here is more convenient than being in Cambridge, although I'm in Cambridge half the time. So, okay, so some stuff that we're interested in, kind of backgroundy things, which talk about. One is high throughput, low latency in data centers. So I mentioned a couple of things we built for data center for virtualization, but it now turns out that the one of the bottlenecks for a lot of large-scale computation, that a lot of big data science-y type computations hit, is something that doesn't sound like sort of really fundamental research, but the latency across the data center sometimes is sufficiently high that if you're doing a distributed computation which has some kind of barrier synchronization step, like a MapReduce or Spark or Naiad or a whole bunch of things, if there's any step which involves RPCs between everything or a shuffle phase, then that's the gating function for each phase of the computation, each epoch. And actually speed-ups there really help. And so one of the things, we have a student who's just finishing his PhD in Cambridge. His defense is on Thursday. just before we all go for a Christmas dinner in Cambridge, so hopefully he's going to be happy. And he got 100-fold speed up in latency in the data center by bounding the tail of the latency. So he doesn't get 100-fold speed up for every packet. But the problem is if you have a 10,000 node computation, it only takes one of them to take a millisecond instead of 100 microseconds or 10, whatever your latency is, and that the whole computation is then slowed down, unless you're clever about throwing out outliers, and that then means the programmer has to think too hard. So there's a whole bunch of tricks here that you can do for this, and a lot of them you hear about. We had a systems workshop earlier in the year with a bunch of people from all the 5 partners, and it turns out many of them are data science experts who've learned system programming. And one of the things as system programmers we want to do is to not have PhDs burn their time doing that unless they really want to. So we'd like to do it once so that everyone gets the advantages. Okay, rather than have some NLP expert or some really clever high dimensionality mumble stats person struggle with a whole bunch of offloading processing into a GPU or some other thing. So those are things we'd like to do. Down here is, if you look online, you'll see the slides. There's a link to a seminar we had at Schloss Dagstuhl. Many of you may know this place in southern Germany, which is a very, very cool place where you can arrange 3 or 5 day seminars. And we had one on low latency in data centers. We had many people from big companies and research labs. And one guy, Jon Crowcroft, who is a Stanford prof and has done multiple cool things, actually forced a rather nice result in that seminar, which was to write down what we thought were the things we'd solved that we should just be part of everyone's toolkit and things we haven't solved. Another thing I'm interested in is somewhat different from that, which is decentralization. So I'm very interested in what happens when you, instead of putting all of our personal data into central cloud services like Facebook or the NHS Far Institute data centers, we keep it all ourselves, and we keep it on small devices in our pocket, in our car, in our bicycle, in our home. And maybe we encrypt and replicate that for backup disaster recovery reasons, but it isn't any of Zuckerberg's business, it isn't any of Google's business unless I want it to be. And it's okay for my GP to access the data, but I give them credentials for access, I give them keys, I can revoke them when I change GP, or I can give a sort of a broad access to paramedics in an emergency for my healthcare data, and this should be true of all data. So we're quite interested in building systems for this, and we actually have a number of projects. We just finished an EU project which was doing that, which allowed you to do some kind of analytics on encrypted data. So if you're into homomorphic encryption, partner in that project, and Eurocom in France did some very cool stuff in that space. And there's expertise in the Turing, particularly, for example, George Denitzis, who's a very cool guy from UCL who does that kind of thing. So that's kind of interesting. Of course, there are lots of good reasons why there is centralized data in some places, but there also there's a sort of move to decentralization. In fact, the whole of the Estonian digital government services is decentralized and owned by users. One of the reasons for that is they get terribly worried about the Russians walking in any day, and they'd like to all just be able to leave when that happens. The Russians get nothing. They also have disaster recovery arrangements with 2 other countries, so it's quite an interesting approach to the world. You can become an Estonian digital citizen, by the way. Anyone can. It's very cool. I think that idea should be extended to the EU for those of us who think we'd like to stay there. We could just do it, right, on a one-by-one basis. The other thing we're doing is a couple of projects which is nothing to do with Turing, but maybe. We're deploying community mesh networks in developing countries. This is a very broad project with many other people, and this is basically how do you provide free internet access out of thin air. We have a partner from Spain who has a community network called Guifi, which has 50,000 homes on one community mesh network, and we've just done a deployment of a similar thing in Malaysia, and about to do 3 African countries, small areas at first, and the idea is to build a sustainable tech for people to we leave there. Okay, a data science thing I've been doing for 25 years is measuring networks. So we build networks. I was involved in internet building, and we measure them, and we want to know how well they're working. And so we basically log lots of packets. And to do this legally, you have to avoid breaking the law on intercept. If you're a network provider, if you are, say, Telefonica or British Telecom or AT&T, then you can do this for the purpose of optimizing your services for customers. So we built some systems for logging everything. And of course, you have to then build some clever indexing systems. So if you log all the packets on a network, then you need a network, the speed of the entire network, to get them back to look at. So we built a system which unfortunately ended up being the thing the NSA used to spy on everyone, which is a bit sad. Sorry about that. Anyway, so if you're interested in network measurement as a data science problem, the go-to conference is called IMC, Internet Measurement Conference. It's actually in London next year. And it's very interesting. People build stuff, and they do very clever inferencing. You know, for example, you're interested in what is the source of a denial of service attack? Is it the toasters and fridges or webcams of the world, or is it actually, you know, some scripts running on some exploited machines which have got, I don't know, Windows vulnerabilities or whatever? And people care about that stuff for obvious reasons. So, and there's a very interesting, again, looking at privacy. If you want to share the data, which a lot of us do, so we log a lot of data when other people look at it because they're cleverer than us at stats. You really care about anonymizing the data, sort of de-identifying it, very similar to healthcare problem, although lower dimensionality usually. The packets aren't as complicated as a health record for a person. So that's but there are interesting challenges because the data is often graph structured because you have communication patterns, or you have the topology of the network or the applications of the users. And anonymizing graphs is, I believe, an unsolved problem. I've seen papers on it that we don't believe work. So it's quite difficult to share data that allows you to extract effectively the graph that represents all the communication, especially if it's a time-varying graph, and making that so you can share it without re-identifying nodes is hard. We have a bunch of other funny projects I talked about when I was doing a bigger talk over in the British Library fancy conference centre that I think would be fun things to look at. So these are just like taste of things, you know, if anyone's interested in this kind of thing. The Zika virus is an interesting thing because it's a two-population epidemic. You know, the mosquitoes catch Zika from people, and people catch Zika from mosquitoes, and also from other people. And if you were to measure the encounter rates between people and mosquitoes, which you could do with smartphones, you could crowdsource this by listening to the audio on a phone. The Zika-carrying mosquitoes are a female of a particular species whose wing beat is actually around middle A, so 3 below middle C on a piano. About 400 hertz, and you could easily detect that. You could actually even work out the proximity or the approach and departure. You wouldn't tell you that you've been bitten, but you could do some statistics to do ground truth and then work that out. Other projects, if we have a fully decentralized data, how do you do decentralized privacy-preserving analytics is interesting. Queries over 35 million databases, kind of tricky. When we have Effie and other people who are experts in thinking about that already, but perhaps less databases with more data in each one. We have access to interesting data from partners in the Turing, so the HSBC or the Financial Conduct Authority, and looking at the resilience of graphs for trading would be an interesting thing. If you alter the edges, the strength of edges in those graphs would be a fun project. And the last one I have is I have a PhD student working on, which is how do you tell if something on the net in Twitter or Facebook is a person or a program? It's a Turing test, right? So I thought that would be an appropriate thing to throw in here. And it turns out it's not as hard as a Turing test because actually most behavior on Facebook and Twitter is pretty stupid. It's not a general intelligence test problem. So it's not actually an AI thing. But detecting it is a machine learning exercise. So you find signatures that are typically Twitter bots. There's a meta problem, which is the evolution of social media, which is almost all social media evolved from being useful to being swamped by junk. Adverts on search and on Facebook gradually overtake the useful content. Spam on email long ago overtook the useful content, and we imagine all systems go through this. So the meta project is to look at what is the evolutionary pattern that causes that across these systems. It would be fun. Okay, why are we all looking at this? And this is getting to the topic of things I'd like to do. We've got all this cloud data analytics. It comes out of hype. The hype came from Google, and it happened from an accident of what Google did. So when Google started, they had PageRank. This is not an original algorithm, and actually Karen Spot Jones developed information retrieval algorithms that look exactly like PageRank in the 50s, really long time ago. But they nailed it very nicely at the right time, and this was a search engine that was relatively hard to game compared with previous search engines. But the real light bulb moment was when they realized that once they had the ranking ungameable, then clicking on the results of search turns into money, because effectively it gives you market research and an ability to do a targeted ad. So then you get the gold rush. And in the process, they built a bunch of very big data centers because they had to index the web, which means they had robots that went across the web, retrieved information, and then built these, essentially, the graph with counting the inlinks to any given page. So it's a kind of well-known thing. So, and in the process of doing this, they created this world where hyperscale is cheap. But essentially, this quote, does anyone know who that person's real name is? Quantity has a quality all its own. Do you know who said that? Does nobody know who Josef Vissarionovich? Yes.
I think he nicked it from the Mongols.
I believe he did nick it from the Mongols, but that's actually Stalin. This is his real original name, so I can't pronounce Russian names. Anyway, sorry, but the point about this was that Google discovered that effectively when you buy commodity PCs, but you buy 1 million of them, you get a really good discount. And so you get sublinear price. So you get performance increase. And this is why we're looking at data centers that outside of high performance computers, which are specialized facilities, which cost a lot because they have very large memory systems and very, very tightly coupled low latency interconnect. Your classic thing where you go buy a bunch of Ethernet switches and connect together a bunch of commodity racks full of PCs scales really nicely. So now you deliver trucks load of these things and it's cheap and cheerful. The other thing is that hyperscale systems became easy to program because people then built tools to make it easy to program because they kept coming up with new apps. So not just an app for your phone, but an app for a 10,000 core system. You want it to be easy to build. And so, we've seen, MapReduce Hadoop-like systems. We now see Spark R, which is probably a better match to some people's sort of requirement for stuff in the Turing. But then there are other things coming along all the time. And people, of course, then add domain-specific languages and APIs to this, including sort of spreadsheet, visual programming, and other systems to make it easy. Some of these systems, particularly Spark, mask failures in the network, so you don't have to care about the problem of dealing with the fact that in 1 million nodes at any given time, some of them are always going to be broken or fail halfway through. That kind of thing came out actually of probably render farms in movie making. But anyway, Google reused it, Amazon reused it, Microsoft and Azure reused it, and sort of this technology is now. So you have cheap stuff which you can rent by the thousands of cores, and we have access to that here for agreements with Microsoft and Azure, and also stuff we can probably do with other people and so on. Okay, so I'm going to just quickly go before I run out of time, which I have about 5 minutes or something left.
Yeah.
10 minutes. Oh, okay. So this is something that we've been forced to look at, which is confidentiality and integrity. And there are sort of several different pieces to this. But the bottom line here is that the encounter with the Financial Conduct Authority and with the Fire Institute has been to reinforce a realization that we do not have an option not to, we have to worry about privacy. Privacy is the law. And this is to overthrow a statement by somebody, I think it was some Microsystems back in the day. He said, privacy is dead, get over it. Well, he's wrong. Because we actually, in Europe, we have GDPR coming in, which will come in the UK because it will come in before we leave. And actually, it's aligned with data protection law anyway. And that's interesting. There's an interesting conflict with lawful intercept and the new Investigatory Powers Act, but let's get onto that in a second. But the point is we have the capability to look at this data, but we have the requirement to not leak the data if it is to do with finance, or if it's to do with health, or it's to do criminal records. If at UCL, they have a very good crime research center, and you can't just let anyone look at that. It's very, very strict. In fact, the penalties for abuse of this are like you lose your job, the company doing it or the organization doing it gets fined, and people go to prison potentially. GDPR penalties are actually pretty serious. So we really care about that. But on the other hand, we have systems where we can put all this data in one place. A petabyte of storage we heard in a system workshop 3 months ago here is about $1 million. Petabyte flash storage, sorry. That's like, that's all the UK patient records for the current data, not the historical data. So that's not very much money looking at NHS budget or whatever. So we have a sort of interesting thing there. So we're interested in how do you do queries over these systems? And I'm not the expert here. We have experts here. I've mentioned Effie and other people. But as we see people link up the databases so that you can do queries over multiple databases, it's potentially a problem. And so one of the things is that the first point is that when you query over multiple databases which have different schemas, potentially you can generate tuples that combined with other tuples could then lead to a revelation of stuff you're not meant to know. I think that's right, but you'll correct me, roughly. So that's one problem which may be possible to fix by analyzing the queries and knowing the schemas and knowing enough about the data. Second problem is data dependent. And so that's the contents, which is that if you do a query like, who in this city block has sexually transmitted disease and is over 2 meters tall, there's probably going to be 0 or 1 people. So I deliberately chose 2 meters. Nobody in the room 2 meters tall like that. But so the point is there are queries for which there's a very small number of answers. And so we heard yesterday from Cynthia Dork, if you were there, fantastic talk about differential privacy and how we can tackle that kind of problem by looking at the bounds in the data, and actually looking at what happens when you combine data from multiple data sets as well. So it's kind of there are ways to tackle this, which come out of Microsoft Silicon Valley Labs originally. And there are ways you can fuzz the data. You can add fake records. There's work at Harvard by people who realized when they were doing statistics over MOOCs that they could be accidentally invading the privacy of people by revealing that they had very good or very bad marks in something, or they gave up a course halfway through, or whatever, that their employer was paying for, or whatever. So those are issues and so on. And of course, then there's this problem of combining this data with external databases, which we may not know about or we may not have predicted. So famously, Massachusetts released a bunch of the state of Massachusetts released healthcare data which allowed people to re-identify records of people, the governor of the state and whatever. In fact, Uber data was used to re-identify a film star who was going from a hotel in New York to the premiere of the movie he was in. It was pretty obvious that could only be this person. So I think it was Brad Pitt, actually, but anyway. So we have an issue with that. So we have a responsibility to not do that, either revealing data to people who are working on health and have been given access because they want to do some public health research or look at epidemiology or whatever it is, or, but they're not supposed to see individual results. Or obviously, if it's the GP looking at their patient record, that's different. They're doing a query, which they've got a role that says they're allowed to. That's not an issue. If outside that role, they're a statistician, we need to be cautious about it. But there's another thing, which is, of course, the health service would like to reduce costs. And so maybe they'd like to enlist the use of the cloud because that would be cheaper. But can they use the cloud safely? Can you really upload data to Google? I think not at the moment. I think that's a very bad idea. It's almost certainly very illegal. The Information Commission did not actually shut down the company that did that for the NHS, but probably should have. In my view, they moved data into a service which was in another country which doesn't have oversight or any redress if something bad happens. So could we fix that? Well, maybe. And this is where we're proposing to work with GCHQ and Intel, using a technology also with some people at Microsoft in Cambridge and a lab there, and Imperial College in London, using a technology called SGX, which is secure guard extensions of Intel processors. We could also use the ARM Trustzone, which allows you to execute code on an untrusted platform. Because below the untrusted system platform, there's trusted hardware. And the trusted hardware is trusted because the keys are not owned by the data center operator. And so that partitioning of the problem space allows you to do things. There are some shortcomings in SGX, notably, as Cynthia Dwork observed yesterday, Intel don't provide a source of random numbers, which does cause us a bit of a headache at the moment. We may need to do a fix to that. But this would allow us to do some cool things like outsourcing health or financial or criminal record data processing onto the cloud, therefore reducing costs of those agencies. And a lot of other people, like banks, the HSBC, would love to do this. They would reduce costs a lot. At the moment, they don't care that much about costs because they have a huge operating budget. But, you know, the department head in the IT, whatever, does. So privacy is sort of hard. We haven't solved this problem. This is a proposal at the moment inside the Turing, which we want to do and people want us to do. But we are working on this tech. The last thing I'll mention, which is something I'm going to talk about in a company tomorrow, is GDPR requires you to explain what your machine learning is doing. And I think some people here are aware of this. And explaining what your machine learning is doing is quite easy for some classes of machine learning, quite difficult for others. This is a challenge to people out there who do deep learning. So it's not clear to me how you explain what a hidden layer neural network perceptron magic thing does. Whereas if you've got a Bayesian inferencing system that's inferred some latent variables, it is clear what it's done. So then the boring examples here, if you infer that from the fact that somebody's driving a pink car and doing it in the afternoon outside schools, therefore we can give them cheaper driving insurance, you're not allowed to do that in European law because that's inferring that it's a woman, likely, and you're not allowed to give an a priori discount. You can give a discount because they have a track record of safer driving. But but that if you had a machine learning system that was random forest or Bayesian, you could work that out, that it had done that. If you had a system that was a neural net, you might not be able to. As far as I know, people don't use neural nets for that kind of problem because it is a relatively simple statistical problem. But it'd be interesting to see how far one could push that. Okay, and there's an interesting thing about revelation from ground truth data is tricky. So there you go. There's a bunch of things that I've done from some of my colleagues in the past, lots of stuff there. There's some stuff we want to look at right now and that are part of projects, and we have to look at, and then some stuff we're going to try and look at in the system support for privacy, which is not really directly Turing, but if you do it, it will enable people to make progress in other things, I think, more easily, so they'll get at real data, which has really interesting statistical machine learning challenges in, which will be difficult for us to get at. We know, for example, in the NHS Scotland, that the time it takes to get ethical and technical approval to run a query, I think is on the order of 6 to 9 months. And so that process is incredibly slow. I mean, you know, basically you've kind of finished your master's or your second year of your PhD before you get the data to do it. That's kind of, we could start a pipeline going, but we don't know what queries to start asking. We need to compress that some. And some of that is social, but some of it, you know, these technical things would make it easier to do some things with. So that's it, and I think we have 5 for questions.
Have you looked at the problem or thought of the problem of handling, so when you have the distributed data, so you're not centralizing the data store, the possibility of an adversary influencing the analytics that you might do. So I'm sort of wondering about machine learning in the presence of an adversary.
Oh, right.
Whether that's more likely in this distributed setting, decentralized setting.
That's an interesting, yeah, okay. I would sort of claim the adversary now has to tackle, if it's sort of UK households and you're doing, you know, fridge machine learning, fridge analytics for Tesco's, then they have to go and undermine a significant fraction of 35 million servers. So it's a challenge for them that's probably harder than undermining one centralized database where the fridges were sending all their stuff to, which demonstrably frequently happens, where there are leaks of everyone's data from one of these central databases. But it's a nice challenge. I suspect also you'd be able to do some clever inferencing that something fishy was happening. So you could imagine having a fraction of your nodes hardened better than others, which would cost more, and then you would use those as essentially as a baseline for comparing. So that's something we do sometimes in malware detection inside the cloud, where we have a fraction of machines which run super fast, but then pretend they're slower and detect injections of malware, and then find signatures. This was the thing with Microsoft a few years back, and then send the signatures around to warn everyone. And so you could imagine that would be a really nice project, though. That's a really cool idea, actually. I mean, yeah, that's a sort of decentralized system adversary. I mean, in another sense, if the adversary is an IoT hacker, they go right to the source of the data, the fridge itself, which we know people are doing because the security is terrible there. But then you could do sanity checks on, you know, what is this fridge telling me? And if you're Tesco's, you could data mine your club card data or Boots, and you would look at the distribution and say, this is something that would actually be really useful. Be a malware detector for fridges. You know, you combine the central and the distributed thing. There's legs in this. I hope the security people here are listening. That's a nice little project. Cool, very nice. That's a really nice question, actually. Thank you. Well, we have this work ongoing in that decentralized approach, so we should take that on board. Cool, thanks.
The Intel thing is very nice, but how far do you think you can trust that? Because
yeah,
maybe a random bit or
sure. Right, I think it's raising the bar for the adversaries in that sort of, that is a centralized cloud sort of scenario typically, and it's making it harder for the attacker. Of course, there's the backdoor which you might think the U.S. government has put in, but that's for intelligence. It's not to undermine businesses, so you know that might be there. Plus, you can source ARM processors which have a similar technology of trust, which actually has been shown to be quite hard for the US government. For example, FBI versus Apple was around the enclave, which is the same idea on the iPhone, and extending that. And you could get your ARM chips made in China or Malaysia or Australia or Wales, and so you could mix them. But I mean that is a worry, and yeah, I mean
do you want to build your whole security and privacy on top of?
No, I wouldn't. In fact, I had a conversation with George Denises, who's here on Mondays usually, and he actually has another approach which we could use as well, which relies only on integrity checking, not on the confidentiality, but builds a confidentiality system on top of that using some zero-knowledge tricks, which I don't claim to get, but we think there's a way forward. So he's going to help out with that as a sort of alternative.
So sometimes, right, the more you make people do to get in,
yeah,
the better it is.
Yeah.
Rather than a monolithic system.
Yeah, no, I agree. I mean, right, I would prefer to have a kind of a large gene pool of solutions so that no one system is, yeah.
Thank you.
Yeah, great, good points.